Section of the notes will look at the optical properties of metals. Significant difference between insulators and metals is that metals tend to conduct to some degree or other, and the reason they conduct is that they have free electrons or free charges within the material, which for metals are electrons, whereas in the insulators the electrons are all bound to individual atoms holding the material together. In the metal you have electrons which are doing the same job. You've got some electrons which will be holding the material together, fixed in location, but you'll also have extra electrons, and these are electrons which are free to travel within the metal. So if we apply an electric field across that metal, then what we do is the electric field generates a force across a force on the electrons, and the electrons will start to flow, and that will make a current. So the current density, J, depends on the size of the electric field. And remember, the electric field for us is an oscillating light beam. So the amplitude of the light beam is oscillating with an electric field. So the proportionality, the constant of proportionality, is referred to as sigma, which is the conductivity. So better conductivity means that you'll get more current being produced for a smaller field. So in an insulator we don't have any free charges, so the conductivity is 0, and for metals it's non-zero in some finite number. For a perfect conductor we would have that the conductivity is infinite, and so for the free electrons or the conduction electrons, there are no restoring forces, so there are no springs attaching it to any particular nucleus, and since we have no springs, there are no natural frequencies for it to oscillate at. In real metals, we have a way of this. We can think of the analogy of Brownian motion for molecules in a gas. So if we have a box of gas, then the molecules will be moving around in random directions at random speeds, and will bump into each other, and all sorts of interesting things will happen. In metals, the conduction electrons behave like that. They are free to move inside the boundary, within the boundaries of the metal, and there will be random collisions between the electrons themselves. There will be random collisions with the underlying lattice of the material, and there will be collisions with various imperfections which might be within the metal. So these collisions convert the electromagnetic energy into heating, into what's called Joule heating. We have the electric field drives a current, moves the electrons around, the electrons bump into things, they lose energy, and that energy is then transferred into heat, or if we think about any temperature increase or temperature decrease, then what we're thinking about is how much vibration or how much energy of movement's a kinetic energy thing. For the lattice, for metals we tend to have a lattice structure, a crystalline structure, or a polycrystalline structure, and the energy of the that's going to be transferred, the energy which is being input, has to match up with one of these modes of oscillation. So if we remember back to the phonons, we had energy level 1 and energy level 2, and we said that if a photon is to be absorbed, then the energy of the photon must be equal to the gap between these two energy levels. Well, in this case, the energy of the electron is carrying has to again match the gap between various modes of oscillation in the lattice, this now, and we call them phonons. So phonons are just a measure of lattice vibration. So let's think about waves in metals. If the wave equation that we had before for the insulator didn't have this term involved. Okay, we just had that the second derivative with respect to space was equal to a constant times the second derivative with respect to time. But now, in the metal, we have another term, and that term is a dE by dt term. Okay. So it's the first derivative with respect to time. Now, going back to second year maths, you'll remember that if we have a second order differential equation, then the d by dt term is related to the damping within that driven damped oscillator. So the last term is a first order derivative, and so it's related in some way to the damping force within the oscillator model for insulators. It's kind of related to that. We can compare it to the damping force in the oscillator models. So this dE by dt term generates the voltage that makes currents flow, and since the material has a resistance, then the light gets converted into heat. Okay, so this time the energy is being lost by moving the electrons around inside freely within the metal, and those electrons then bumping into the lattice of the metal structure and transferring energy that way. What we need to do is we need to find a solution for that equation so that we can find E as a function of time. And we can simplify the equation if we make a substitution, and that substitution is to say that the permittivity is a complex quantity. So if the permittivity is complex, remember, then the refractive index will be complex as well. And we saw that when we had a complex refractive index in insulators, then that implied that we had absorption. So if we have a complex refractive index, we have absorption. And here's our assumption that the refractive index is a complex quantity. It has a real part and it has an imaginary part. So we can guess again, we can use our guesstimated solution that it will be some sort of sinusoidal variation. And we can rewrite that expression because we have a relationship between the refractive index and the frequency, the angular frequency, and K. So rewriting that expression, we end up with an equation here. And you can see that again, it's just cosine of, and then we have our angular frequency taken outside, and this time we have the refractive index here. Okay, so if we substitute in our complex refractive index, then because we've got exponentials, then we can simplify things fairly straightforwardly so that we have our original amplitude E naught. We have an exponential term here, which is a real exponential and it's negative, so that's a decaying exponential. And we have e to the I something or other, so that's an oscillating, that's a cosine type or a sine cosine type oscillation. And so we can simplify that equation here so that we have an oscillating part, the cosine term here, and we have a negative exponential part, which gives us a decaying wave. So as the light travels into the material, what we'll find is that its amplitude will die away very quickly, exponentially, and because the intensity is proportional to the amplitude squared, what we'll find is that the intensity of the light as you travel in to the material will decay away sharply again. So the real part of the refractive index looks just like the normal refractive index that we've seen before, but the amplitude of the wave is then modulated by this negative exponential. And as I say, because we have that the intensity is proportional to the square of the amplitude, then we have an expression for the intensity given here. And what we're going to do is we're going to take all these terms, the 2, the omega, the ni, and the c, and lump them all together into one constant called alpha. And that alpha will be called the attenuation